In this video, we're going to look at PD plus. So if you remember back to when we did PL, we said that not all P could be symbolized either like this or like this, right? Either as not for all XP, right? Or as there is an X that is not a P. And we also said that not any P could be symbolized two ways too, right? Either as it is not the case that there is an X that is a P, or as for every x, it is not a p. So PD plus is an extension of PD that includes the quantifier negation rules, which are basically just these rules here. They're rules for dealing with negated quantifiers. So you can take sentences like this and turn them into sentences like this that have inference rules that you can apply to them. So these are the quantifier negation rules. Um, if you have a negated universal quantifier, you can turn it into an existential, um, and vice versa, right? And then if you have a negated existential, then you can turn it into a universal, and vice versa. Um, Basically, what the rules say is this: you can move a negation sign across a quantifier either way, right or left. And when you do that, then the quantifier changes. So if you move a negation across a universal, then it changes to an existential. See if you're going this way here or this way here. If you move it across an existential, so you're going this way here or this way here, then it turns into a universal. Um, and technically, PD plus also adds all of the rules of SD plus, which are not technically part of PD, but you've probably already been working with those. The quantifier negation rules are replacement rules, which means that you can apply them to subformulas. So, for example, you can do something like this, where you start off with the negation over here, and then you can successively apply quantifier negation to apply it to successively smaller subformulas until you've changed around all of the quantifiers and moved it as far in as you can get it with quantifier negation. Um, in this course, we don't work with a lot of multi-quantifier sentences, so this is not the sort of thing that would come up. But if you go on to do further logic courses, this is like this exact move is something that you would actually do quite often, where you start off with negating a sentence that has a big string of quantifiers in front of it, like for negation elimination, for example, and then you take that negation and just shove it all the way inside the sentence as far as it will go. Let's look at some examples of working with PD plus. So if you remember back from when we were doing symbolization, we said that if you have no F's or G's or something of this form, you can symbolize it either like this or like this. So we'll go through and we'll show that these two are equivalent. Now remember, to show that two things are equivalent in PD or PD plus, right? What you need is you need two derivations. So we would need one that starts with this sentence and then ends with this sentence, and another one starts with this sentence and ends with this one. So we've entered in this sentence as an assumption, and then we'll get down to this one. Okay, so the first step here is we'll use quantifier negation to convert that existential quantifier into a universal so that we've got the quantifiers the same. The quantifier here is the same as in our goal sentence. So it's 1qn. Then we've got a negated conjunction inside the quantifier here, and we're trying to turn it into a conditional. And we can actually do that. The way that we want to do it is by going through a disjunction first. So we'll convert this into a disjunction and then convert the disjunction into a conditional. We convert it into a disjunction using De Morgan's. So we'll go use De Morgan's to turn this into not fx or not gx. Oops. There, to De Morgan's. And then we can turn this into this with implication. Okay, so that's this direction. Now, to show the equivalence, what we also need is a derivation that starts by assuming this and then gets to here. Note, though, that in this derivation, we only used replacement rules, right? Quantifier, negation, De Morgan's, implication, they're all replacement rules. And replacement rules are all reversible. So the other derivation is actually just going to be exactly the same as this in the other direction, right? You just go through exactly the same rules, the other way. So the other derivation, you just take this thing and, flip it over, basically. So we're not going to bother writing that out here. I'll write in the scope line later too. The next one that we'll do is exercise 10.3E1D. So we'll show that this set entails this sentence. So we've written out the set members here, and then this is our goal sentence right here. Now, it's a negated existential sentence. So the immediate thing to jump to would be to use negation elimination, right? So we would assume there is a y, not fy or hy, for negation introduction, and then go from there. But the thing is, then is the next step after that, though, would be, because what we'd have is a subderivation starting with this. What we need to do after that is use existential elimination. And as you probably noticed by now, existential elimination and the negation rules don't play great with each other, right? Because if we derive a contradiction directly within this subderivation, that will not, because of the fact that it's in a separate subderivation from the original negation introduction one, that doesn't allow us to discharge the negation introduction subderivation. So then we would have to use the principle of explosion to, probably derive the opposite of one of these and then pull that out of the subderivation. The whole thing is just complicated, right? We can save a lot of time by just trying to avoid that. So what we'll do instead is we'll actually get this through quantifier negation. And we'll try instead to derive this sentence here. And this is a sort of a feasible goal because of the fact that we've got two universally quantified assumptions already. So, given that we've got two universals here, getting a universal goal is probably not that implausible. So, since this is a universally quantified sentence, the most likely way that we're going to be able to get it is through a universal introduction. So we would then derive this here for some constant, and then we'd be applying universal introduction to get it. So let's just assume the constant that we're using is a, because that's kind of the one that at least that I always use. So now we're going to try to figure out how we can get this. Why don't we go back here and start working top down? We know that we're trying to get a sentence that involves a, so let's do universal introduction or universal elimination for these two sentences for the constant a. I should put in the line number there. Then this is 2, universal elimination. And now, that has both f and h in it. So let's just conjoin these two. So we'll get fa and ha from 3 and 4 conjunction introduction. And from there, well, there is a rule, right, for converting conjunctions into negated disjunctions. That's what De Morgan's does. So we're going to get this then through De Morgan. We need one intermediate step, though, remember, which is that because of the fact that this has the negation in front of it, we're going to need to have two negations in front of this in order for the rule to technically apply. So we'll add the extra, we're going to use double negation to get these two here. So we will have this. Then that's in the right form for us to apply De Morgan and get this. And if you go through and look at the official way that the rule is described, you'll see that that's exactly how, right? That's what you would exactly what you would need to apply De Morgan to get that. Then this is coming from line 7, and then this is coming from line 8. And that works out to be a much shorter way of doing this derivation than trying to set up all the subderivations using negation introduction and then existential elimination. If you can just do the quantifier negation bit, it saves a ton of time here.